Hi, this is Albert Lee doing Lab 6 magnetic braking with Faraday's law. So what we're going to do for this lab is basically find out how Faraday's law affects moving magnets with inside a conducting surface because it basically creates a change in magnetic flux. So what is Faraday's law? Is right here. A change in magnetic flux makes an EMF, and an EMF slash electric field is directly related to current, which makes a force. So the left, you can see the equation right there with the change in magnetic flux on the right. B dot product of dA, which makes the EMF. Now for our specific situation, the B is defined, or the change in magnetic flux, like the whole thing on the right, is defined with that equation in the bottom right from the pre-lab. Now the magnetic force can be defined as I slash the current cross product of L and B. Now L for this situation is just the rate or circumference of the tube, which is 2 pi r, and then the formula for current is I equals EMF divided by R. The magnet is supposed to be uniform and the same from lab 3 in our assumptions, and then also the tube is supposed to be ideal and consistent all throughout. Now the preliminary findings is that the average fall time was 1.18 seconds. This is using cameras, and then the predicted time from the glow script is 0.88 seconds. Now, to get that predicted time, our script up to 1.18, we had to raise the magnetic dipole moment to 4.815 amperes times meters. So this is our procedure, what we did. I mean, you can see the magnet right there being dropped down the cylinder, and that basically creates a change in magnetic flux because of the moving magnetic field. And you just drop it down a conducting tube, and that'll do the trick. Now here's the procedure. Basically, I mean, it's pretty easy. You just drop the magnet down the tube and record how long it was in the tube. But then you make a glow script computational code to model the lab statistically and compare the two results. So the average fall time through the tube was 1.18, like I said before, and then we input all these stats about the tube and the magnet, and we got that using the original magnetic dipole calculated in lab 4, it was 4.116 amperes times meter squared. But now in lab 6, we had to up that to 4.815 to get the realistic time of 1.18 seconds through the tube. So here's the glow script. It's pretty easy to look at. I mean, you're just initializing the stuff right here, the magnet and the tube. Then top left is the function to make the magnetic field. And then the top right is the function to calculate the magnetic flux. Then you're simulating the drops. And yeah, that makes this. So on the left, you can see the graph of the modified magnetic dipole moment of 4.8. And then on the right is what we calculated from lab 4. And at the top, you can see how the magnet was dropped through the tube. Now, using the dipole from lab 4, it was 14.5% lower than the one from this lab. So it's safe to say that the magnetic dipole from lab, it says 3, but it was actually 4, is most likely smaller than the true value. It's probably somewhere in between, but yeah. So some error that could have happened was definitely friction from hitting the sides and then air resistance and dropping it, obviously. And also, obviously, human error with just timing and seeing how long it was in the tube. And then also, the tube was most likely not a perfect conductor. Now, what if the resistivity was reduced to nearly 0? Since EMF would stay the same, but the current is inversely related with, EMF equals I equals EMF over R. This would increase the current a lot, and in turn would increase the force with that force equals current L across B, and make it fall slower. Now, if there was holes in the tube, however, this would disrupt a lot of the Gaussian surfaces, and the induced current would be greatly reduced, and that would reduce the force, allowing the magnet to fall faster. Thank you.